Howdy, Precal 12B. So today we're kind of moving past the concept of limits, and we are getting into something that is going to become rational functions. However, as kind of like a sadly still not quite into the textbook yet, but as a little bit of a primer and lead up into rational functions, we're going to talk today about reciprocal functions. Now, reciprocal functions are, you should have a pretty reasonably good idea about what a reciprocal function is because you know what a reciprocal is. So if I said, for instance, we have the value 2, what is the reciprocal of 2? If you don't automatically kind of feel you know what to do there, you can always write any value if you would like to by changing it to have a denominator of 1 kind of visually. It doesn't change the value of what you're looking at. And in the case of a reciprocal, you're always writing it as a rational expression that where your numerator and denominator are flipped from what they used to be. So in the case that we had originally, we have 2 over 1. Now instead we have 1 over 2. If you started with 3/7 to begin with, the reciprocal would be 7/3. And so that's pretty, it's just a reminder of what a reciprocal is. And so now we're going to be taking a look at reciprocal functions, which are basically just the same idea. Instead of having just a numerical value, we're instead going to have functions. And so if g of x is a reciprocal function, it is going to be said to be the reciprocal of some function that we already know. So, I mean, obviously you can have something that's currently a reciprocal function, and the reciprocal function of that function is going to be your original function, but we don't want to get all kind of wonky in terms of the way we explain things like that. So we're going to say that if we have kind of our base set of functions right now that we are comfortable with and we understand, we're going to be able to take the reciprocals of those functions and get an understanding of what those would look like and kind of the behavior that they would exhibit. And so generally, it is true that we are just going to define some g of x reciprocal function as being 1 over whatever the old function was. So that's like writing the old function as f of x divided by 1 and saying that the reciprocal of that is just flip-flopping and saying it's 1 over f of x instead. So just like the examples that I had above numerically, we're going to basically just take your numerator and denominator and flip them. Written beside over here is another way we can write the exact same thing. Now, if I taught you Precal A, you probably heard me complain about the notation that goes along with the inverse. So inverse functions have a notation where the -1 is put in between the function and the argument. That position, for instance, for a sine function, if I just have sine x, it's understood what that means. We kind of have a pretty good understanding there. And sine squared x, that is another way of writing, for instance, sine of x all squared, which is the same thing. It's just sine x times sine x. So all three of those are the same, and that's great. And we can do it with a cube too, and that makes a lot of sense. The problem is that this actually means the inverse sine, which is not equal to 1 over sine x, which is not equal to sine x all to the power minus 1. I wrote that in the opposite order of what I wanted to say. These two things are actually equal to each other. Those are both the reciprocal of sine x. Sadly, the notation kind of seems to maybe not overlap, but it shares enough common features about it that you would hope that it would be true that these things would be equal to each other. But this thing in the middle is special notation, and it means inverse, and we want to make sure that you are very comfortable with what inverse means and how it looks. So switching your x and your y values, think about it as being a reflection across the y equals x line. However it is that you normally think about inverses, go back to your Precal A material, feel really good about them, because Reciprocals, notation-wise, look like they may be the same thing. And sometimes math teachers, people like me, and maybe even myself, will do a slip of the tongue and actually say the word reciprocal when we mean inverse, or the word inverse when we mean reciprocal, and that's bad if we do it. So it's setting a bad example, because those are actually very, very different things. The thinking behind the two are different. I can't remember off the top of my head. I'm sure there's really basic cases or weird examples where you could say that the reciprocal and the inverse were the same. I guess if you have, no, I don't know. I can't think of one off the top of my head. But I'm sure you can come up with some sort of funky example where that may be true. But generally it's not. So think of them as very separate ideas. All right, so we know a bunch of different functions at this point. So we are able to look at a fairly good number of reciprocal functions. And we're not going to study them in great detail. It's mostly if we are comfortable with an original function, how do we assess what its reciprocal is going to look like? So for instance, this one here would be the reciprocal of a square root function. That square root function is just, we, because of our experience, know that square root functions kind of look like this. That would be just like root x. This one shifted, if you remember your transformations, which we haven't touched for a very long time, this is shifted 3 units to the right, so it might kind of look like that. But this is not the one we're actually interested in here. This would be the square root of x minus 3. F of x in this case is actually the 1 over the square root of x minus 3, which is, again, known as the reciprocal of the square root of x minus 3 function. Sine 2x, so that one is instead looking at a sine function. So we start in the middle and go up and down and up and down. So if this was normally going to be 1 period from here to here, so I would have 2 periods in that span instead. So it looks something like that. And so this would be sine of 2x just has a period that's 1/2 the size that it used to be. So everything's condensed like this. And so, we could continue that thing in both directions, blah, blah, blah. That's great. And, but that's not the reciprocal. What g is actually 1 over the function that we're currently looking at there. And we could do that with anything. So we could do 1 over a logarithm. We could do 1 over this thing, which is just a polynomial function. So it's a cubic. Cubic with an intercept is 0, 1, and -1. And so, well, okay, great. So this is the idea of what reciprocals will look like. For us, we're not going to just take absolutely anything that looks kind of like a reciprocal. It has to be something that is just 1 over something we already know and understand how to graph. So if we understand behavior around certain key points, we can kind of connect the dots to fill in the rest of what's going on. And get a reasonably good sketch. So let's just look first of all at the linear function f of x is equal to x. So if we describe g of x as being 1 over f of x, just to sketch that down, we have said f of x is equal to x, and g, that's not a g, g of x is equal to 1 over f of x, but we know f of x is x, so it's 1 over x. So this is probably the most plain looking reciprocal function that we'll talk about. And so this really plain looking thing is what we're interested in graphing. Now, if we make a table of values where x, just your x values, these are just f of x is equal to x. So because that's the linear function, -10 is equal to -10, -1 when you have an x value, because it's just f of x is equal to x, all these values are the same. These values over here are going to be made up by taking the reciprocal of these values here. So this is 1 over negative 10 and 1 over negative 1. 1 over 0. Okay, that's a little bit strange. 1 over 1 and 1 over 10. So I have a little question off to the side here. It says, what are the invariant points? So in this table, it's fairly obvious what the invariant points are. Because if we just are looking for them really briefly, we would find that those numbers change. So that's not going to be an invariant point. These numbers here, I guess I shouldn't be highlighting the first thing necessarily because that's not really important to invariant point. These numbers are the same. So under this particular transformation, the negative 1 that we started with stayed a negative 1. These numbers are not. These numbers stay the same. And these numbers do not stay the same. So we have an invariant point that happens here and here. And the question is that always going to be an invariant point? Well, let's think. So if you have something in fractional form and you're flipping a numerator and a denominator and it's a 2 and a 7, well, that's never going to become something that's the same value because it's now 7 and 2. Well, when you think about all the different kind of combinations of things, 1 and 1, you flip them and it's 1 and 1. Well, what would have to occur for a flip to give you the same thing is for the numerator and the denominator to be the same. But if the numerator and denominator are the same, you can always reduce that fraction to being 1 over 1. Or in the case of them not being the same, if you had a 1 and a negative 1, the thing is that a 1 in a numerator position, a negative in a numerator position, a negative in a denominator position, or a negative out front are all equivalent. So the location of that negative sign actually doesn't matter. So as long as numerically, without worrying about the sign, the numerator and the denominator are the same value, then that's all that's going to matter. So if we have 2 over 2, that's the same thing as 1 over 1. If you have negative 3 over 3, that's the same thing as negative 1 over 1. So as long as everything reduces to 1 over 1 with a negative sign there or not, then you are going to have something that's invariant. For us, that basically means that because it doesn't matter whether it's a fraction or not, we're looking for a value of negative 1 or a value of positive 1 for those y values, because flipping either one of those will still give you always a negative 1 or a positive 1. And those are actually the only circumstances where that will take place. So in this particular graph that we have right here, we have, and this is going to be a gross kind of big blob there, but actually that was less. Oh, I chose the smaller one. That's good. So small. That was 2. Back it up here. So this is the 1, 1 point. So it is going to be 1, 1 for the normal point. But also, it's going to be 1, 1 for the reciprocal function. So it's going to get a point in the exact same spot. This one down here is our negative 1, negative 1 point. So negative 1, negative 1. But for the reciprocal, when we flip this, it's still a negative 1. So it's going to be a negative 1 reciprocal point. It's really important to note that we can speed through and do something where we can identify the one anywhere where you have a y value of 1 and anywhere where you have a y value of negative 1 as an invariant point. They are going to be the same point on the reciprocal graph, and we can grab those really quickly and get the points that we need. Now, this is going to be awful because I can't freehand this very well, and I should have probably put something over onto my page. Maybe I'll just do a really quick sketch of it here, because if not, it's going to become a big mess. So if I have a linear function, just y is equal to x, and I say that right here is an invariant point, and right here is an invariant point. So the question is, do I understand what my function is going to look like elsewhere? So out here, out this way, to the right-hand side, I am going to be getting values like at an x value of 10, it's at 0.1. An x value of 3 would be at 1/3. An x value of 2 would be at 1/2. It's going to be like 1/2, 1/3, 1/4, 1/5, 1/6, 1/7. And I mean, that's really thick because of the one I chose to use the highlighter there. But it's going to kind of go out like that. Now, as we come in the other way, there's this really peculiar thing that happens right at 0 where we don't get a number. We get something that's undefined. Ooh, okay. Well, what do we do when we have something that it doesn't work at the point, but we want to figure out how it works as we get close to that point? Limits. So we could say if we were doing the limit as x approached 0 from the right-hand side of, and really I'm looking for what I've called g of x. So from the right-hand side of g of x, that's the behavior that I want to describe. Now, we could put in numbers like, for instance, a half. Well, that would be the reciprocal, so it would be 2. A third would be 3, and a tenth would be 10. And so the smaller we get, or the closer we get out this way, so a half would be 2-ish, and then a third would be 3, and 4 for a quarter. So it's going to look kind of like this. And we get a behavior where as we approach that value of 0 from the right-hand side, we are going to get positive infinity as being what our numbers are tending towards. Again, we would have the limit as x approaches 0 from the right of 1 over x is what we're evaluating. So it's a positive 1 divided by a really small positive number. That's going to blow up and give us that positive infinity. So it's going to look kind of like that. On the other side of things, it's going to be really similar, except for we're working with negative values. So we have a negative 2 for the x value. It's going to give you negative 1/2 when you flip it. And negative 3 for the x value would give you negative third, negative quarter. It's going to kind of look like that. And then we would be asking the same sort of thing from the other side. Okay, well, this is the limit as x approaches 0 now, but we're doing it from the left-hand side. So of g of x, which is the same thing as saying the limit as x approaches 0 from the left-hand side of 1 over x. And so if we are approaching from the left-hand side, we're actually having negative values. So it's a positive 1 divided by a very extremely small value, but it's negative. And a positive divided by a negative gives us a negative overall result. So we'd be tending towards negative infinity as we take that limit. So as we get closer and closer here, it's going to go way, 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 way down. If we were to take a few random values in the middle, negative 1/2, flip it, is negative 2. And then negative third, flip it, it's negative 3. And so it's going to kind of look like this. And so we get this pretty little graph that goes, well, I'm not very good at now, depending on where the mirror image, it might be the opposite of what I just did for you. It probably is, actually, because I think that was right for me. So it would be more like, woo. I'm not very good at this game. All right, so the idea here is that we get invariant points that are very easy to mark off because they are the positive ones and they are the negative ones. And then we're going to get some funky behavior when we get zeros, because zeros become 1 divided by 0. And depending on whether you're approaching taking 1 divided by a very, very, very positive small number or a very, very, very negative small number as you come in, you're going to have either values that tend towards positive infinity or negative infinity around those zeros. So in this case, we had 1 of each on either side there. And yeah, that's basically our reciprocal function for that goes along with the original y equals x or f of x is equal to x linear function. So anyway, that's that one. Let's take a look at this one here, which was also on the beginning one. It's the that's this one right here, I guess. The shift of the original square root function 3 units to the right. So if I have this thing here, oh yeah, I forgot. I should do that. So hold, and then it becomes straight, hold, and it becomes straight. There, that's much cleaner. All right, so the idea here is that if we go over, and I marked it off that this was 3 up to this spot, then this is our square root function. So it's up 1 over 1. The stretch is all the same as normal, so it'll be over 4 from the original up 2. Because the square root of 4 is 2, and it's just been shifted. So it kind of looks like this. All right, so this is the graph that we are going to be applying a reciprocal on. Now, again, what's going to happen? Well, weird thing happening right here, because what's happening right here is we have a y value of 0, and we just saw that y values of 0s basically blow up when you take the reciprocal of them. We have two choices. It's either going to be blowing up positive or blowing up negative. If we were to say something very careful with limits, we would say, well, what we really want to know is what happens as we approach this value of 3 from the right-hand side for this particular function, which is f of x, again, which is, I probably would have just done well enough to put it in originally, so x minus 3. All right, so let's just pretend we're putting in a value really close to 3, 3.01. 3.01 minus 3 is a positive number. It's 0.01 positive. Take the square root of that. It becomes a little bit bigger, but it's still quite small. The closer we get to a 3, the more that thing is going to approach a value 0. Now, I guess what I really want is the limit of 1 over this is what I'm exploring, because I don't really care about the original function all that much, because we already know how to graph that. So it's, as I said, the inner square root part is going to be getting very, very small, but positive. 1 divided by a very, very small positive number gives us a very, very big but positive. So as we approach this 3, we're going to be getting very, very large values. Now, I think I'm going to hold off until the next time I do a video, when I get into rational functions, but there is this idea of an asymptote that's being placed here. Again, I'm just going to say that there's a tendency for this to blow up and be very, very large and positive. This one right here is at a y value of 1. We know that y values of 1 are invariant points. Y values of negative 1 are also invariant points. There's no negative values here. So I take this one and I make sure I'm going to go through this. Now, I could kind of just cheat a little bit and know that, according to the last one, it seemed to be all nice, smooth, connected stuff, which it's going to be the case here too. Because if we look at the this function right here, the 1 over the square root of x minus 3 function, the only thing that's going to happen to make this not work is if the square root is negative or the denominator is 0. Once you get values that are greater than 3, which is where this thing is defined in our picture, there's no issue with this. You're not going to have a domain problem. So because there's no domain problem, we don't have to worry about it being unconnected, jumping, or doing anything strange. So, because the domain is defined, if it's defined in your numerator, which is just 1, it's defined in your denominator, which is going to be the square root function, then it's also, your function is going to be defined when you do the division of those two functions, which we technically will see in a combination of functions thing that we'll do a little bit later. All right, so I'm going to take this 2 and do the reciprocal of that as well, which is 1/2, so it becomes something around there, and just going to kind of sketch through that. So it's going to give me this particular function that looks like this. All right, so, I mean, just as a, I probably should have done this and set it up, but just as a comparison, let me take and throw this through Desmos, my good friend. All right, so what we just graphed was y is equal to 1 over the square root of x minus 3. Okay, so we could do a little bit of a comparison of mine, I guess this thing right here, versus Desmos, which is this thing right here. My curvature is a little bit off maybe, but overall it's okay. And it probably has as much to do with the scaling along my x-axis and y. Well, I don't know actually. Probably just curved it a little not fast enough. So not as distinct. Probably is a little bit of an oopsie on my point or on my part. But the only way to fix that is to graph a bunch more points. Obviously, I was very, very not very precise on the points that I put into the middle, and that's fine. So that is another reciprocal function. The idea, and I'm just going to pop this back up here, is that we can do this with anything that we kind of feel reasonably comfortable with. So here, this is 1 over sine of 2x, and I'm just going to do this a little faster on this sheet here probably. And so let's label just really quickly some sketchy spots. So we have a sketchy spot here at 0, and here at 0, and here at 0, and here at 0, and here at 0. So those are all going to be awkward when we do the reciprocal of those. Now, to go along with that, we also have some fun invariant points. So we have an invariant at 1, we have an invariant at 1, we have an invariant at 1, we have an invariant at -1, and an invariant at -1, and another one over here. So invariants are going to stay where they are. The blue things are going to have issues, I guess we'll say. So I'm going to, just for the time being, oh, I lost my thing. Kind of label these issues as dotted lines. So I'm going to put a dotted line in there. I'm going to put another dotted line in here. I'm going to put another dotted line. Ooh, that's a little bit off, but I'll fix that in a second. Put one in there, and put one in here, and put one over here. That last one was probably the best of the bunch. I'll just adjust these so that they're a little better. All right, great. So now we know that the behavior around these zeros is that it goes towards something infinitely large. Now, if I were to go from the right-hand side, this is saying the limit as we approach 0 from the right, these numbers that we're dividing by, because they're in the denominator right here, this original green function is in the denominator. They're approaching 0, 1 divided by 0, but it is positive values that are approaching from the right. So it's going to blow up and become somewhere up here, which is positive values. On this side, these are negative values that are in the denominator. 1 divided by negative, so we're going to be somewhere way down here. And we're going to get smaller and smaller and smaller, or larger negative values. We're going to go down as we approach from the left-hand side. Same thing's going to go on over here, except for these are positive. So positive really big, negative, negative really big. And then again over here, negative and positive. And so over here, negative. On this side, positive, positive, negative. All right, so we kind of get an understanding of what's going on in the middle. Now, we also need to, well, if we're going to be really, really loosey-goosey about this, we're basically playing connect the dots. So I need to connect this yellow with this pink with this yellow. And so the most reasonable way to do that would be something like this, probably. Now, if we wanted to maybe make sure the curvature and everything was okay, we do some test points. I'm just going to, for the sake of being a little more brief, I'm going to do something like this. So I'm going to just curve it like this, because these values get really steep towards the ends here. So they're just going to go up, 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 and it gets really close. So it kind of looks like a parabola in a way. Probably more looks like a quartic or a power 6 or something like that. Except for it's never allowed to go past these bars, because once you have become that value, there's no actual value because it's dividing by 0. The closer you get to it, though, the higher you go and go and go and go and go. And you can infinitely or infinitesimally make that number that is approaching becomes this small away from what you're looking for. So infinitesimally small. So it just gets bigger and bigger and bigger. And so we can do that with each one of these. This one is from here to here to here. So something like that. And depending on what you have seen before, you may or may not somewhat recognize what's going on here. So those are going up. These ones here, connect the dots, would be going down. Now I did an okay job up above probably with the curvature. These ones are looking a little wonky, but that's all right. So kind of like that. And on this side, I got a half of one. All right, so for some of you, if you remember the cosecant function, this might look a little bit familiar. If you do not know the cosecant function, then this will not look familiar at all. So I did this one kind of on the same screen, so I'm going to pull up Desmos again, but it's going to be a little harder to do a side-by-side comparison. No, I can't cheat because it's going to... that's all right. I can... well, I'll pull it up and leave it there in a second. But first, we'll fix this. So it will be 1 over sine of 2x. And so it looks kind of like that. And again, I'll just kind of make it so that it's reasonably close in terms of scaling. And so I get this. And we have this kind of nice set of u's that go up. u's that go down, and we have those u's that go up and down here. So that's all we're doing, is we are leaving positive ones as positive ones, leaving negative ones as negative ones, and then being sneaky and kind of using limits to decide what's happening around zeros. So you come into them from the right, come into them from the left, and you really only have two choices, because dividing by 0 is not going to work out, but taking 1 and dividing it by a number that's approaching 0 has either the chance of going and becoming positive infinity, or if those numbers are approaching 0 from the negative side, negative infinity. So we can get a pretty good idea of how that's behaving by kind of applying this idea of limits. We could do the same thing here with the ln x. I mean, I'll just do it really fast. I'm not going to talk a whole lot through this one. I'll just let you see the example, and if you want to look back through it, that's fine. So I'll just say this is a 0. So that's a sketchy spot where we're going to get this infinite limit sort of thing. However, I can automatically say these numbers from this side are positive. So it's going to be like this. And these numbers from this side coming into that are going to be negative. So it's going to go down here. -1 for a value here, positive 1 for a y value about right here at the value of e, if you remember what's going on in a natural log function. And so basically we're just going to play connect the dot like this, and goes down here. It's not as fast as that. These numbers grow really slowly, so this curve declines a little less speedily than I sketched. It's really hard to do it by mouse, which is why I really like doing the doing this thing on my iPad, but I didn't bring over the graphs onto it this time. So that's kind of funky. Ooh, these are going to be interesting though. So this is going to get really small, and the question is, like, if you have something that's undefined initially, can you really say that something that isn't defined, when you do the reciprocal of it, it gives you like an actual defined 0? I'm going to say no. And so in my thinking, if I were to get that there is no value of ln 0, then I'm going to say that there is no value then of 1 over ln 0. So this is going to give me a little hole here. It's approaching values that are extremely large. So 1 divided by extremely large values become extremely small. And there may be some funky ways that this is connected that we don't really know yet without doing some calculus ideas. It's kind of like, how is this going to be curved? And I'm going to say for the time being, let's not worry too much about how that ends up being curved. But we can get an okay sketch of it. So we understand positive infinity, negative infinity. These values become so large that this becomes really, really small. We can't really decide what's going on at that spot because it's not defined. So I'm going to say that there's a hole there. And then over here, positive 1, that's definitely there. And these values get bigger. So these ones are going to get smaller because they're the reciprocals. And again, just because, let's just throw that into Desmos real quick. 1 over ln of x. So yeah, that's kind of got some funky curvy thing going on there, where it gets really, really big, really, really fast, the values here. So it's very steep actually in that section, even much steeper than what I was showing. So it kind of bites over like real hard and then goes up, is what it's more looking like, and then kind of a little more steep on the other side too. Everything else is looking reasonably good. So, you know, if all we're looking for is a sketch to understand what reciprocal functions are looking like, this is going to do the trick. I'm actually going to leave my last example. If you want to do this, I'll just leave it up on the screen for a second. You can feel free to try this one out, and then maybe throw through Desmos yourself, kind of see if you did okay. But we're going to be looking at examples like kind of like this anyway, more specifically when we do rational functions coming up, and I think that's probably a good enough length for now. I hope that you're doing well and that you're not getting too discouraged or bored by these silly things. Hopefully you're able to kind of keep clicking along and doing some learning in Precalc B. I wish you all the best. Take care. Bye-bye.